So I've done this first reaction for you. Single replacement reactions are actually pretty simple, but you have to have an activity series in order to do them. I highlighted this first part of the reaction. So in a single replacement reaction, you have a single element and a compound. That single element is trying to replace something in the compound. And remember that metals will replace metals and nonmetals will replace nonmetals. Well, since aluminum is a metal, it's going to try to replace copper. So you look on your activity series and you find aluminum and there's copper. So can aluminum replace copper? Absolutely. Aluminum's higher on the activity series. So aluminum replaces copper. See where copper is? Aluminum just takes its spot and copper sits off by itself. Now why do I have the subscripts down here? Because aluminum is +3 and sulfate's -2, and you have to crisscross and correctly write a new formula. You can't forget that part. That's a big deal. Okay, over here I've put the equation and I balanced it. 2 aluminums, 3 copper, 3 sulfates, 3 sulfates. Now I want to point out something about this polyatomic. I taught you to put polyatomic ions in parentheses for a reason, because when you get to this reactions part, you can balance them as a unit. If SO4 is together here in the reactant and it's together in the product, you can count it as a single unit. Okay, instead of breaking out 3 sulfurs, 12 oxygens, you don't have to do that. You can just say, well, I have 3 sulfates, and that that subscript down there means I have 3 sulfates over here. So let's check this next one. Magnesium plus sulfuric acid. Well, magnesium's a metal, and there's no metal in this. But magnesium is positive, and so is hydrogen. So what's going to happen is magnesium is going to replace hydrogen in this reaction. A metal plus an acid will always make hydrogen gas. So I know this hydrogen's always going to come off here. If you look, hydrogen is on our activity series. It's just way down here at the bottom. Magnesium's up here. So all of these metals will replace hydrogen in an acid. Okay, so I know that's going to happen. So magnesium is simply going to take the spot of hydrogen, and hydrogen is going to be left off by itself. It gets the subscript of 2 because it's diatomic. Okay, so it's H2 plus our new compound, magnesium sulfate. Magnesium's oxidation number is +2, sulfate is -2, so I don't need any subscripts here. So over here I'm going to balance it. So I get magnesium plus sulfuric acid, making hydrogen gas plus magnesium sulfate. So see, sulfate is together. Okay, it stayed the same on each side. So I can balance it as a whole unit. So I have 1 magnesium and 1 magnesium. 2 hydrogens, 2 hydrogens. 1 sulfate, 1 sulfate. So that equation is balanced with no work at all. All right, so iodine is going to it's not going to try to replace potassium because iodine's a nonmetal. It's going to try to replace chlorine. And in your activity series, you have a nonmetal activity series also, but it's put together exactly the same way it is here in the halogens. Okay? That means that iodine right here is going to try to replace chlorine. Well, iodine is actually lower on the activity series. It's also set up in the same order on your periodic table, so you never really need it. So iodine cannot replace chlorine in this reaction. So you just do that. That means no reaction. So these single replacement reactions, you always need an activity series for. I always have to use that. So let's go down here to these double replacement reactions. Double replacement reactions are where you have 2 compounds and they're going to swap partners. Okay, so aluminum is going to swap with calcium. But what I teach my kids is I teach you to put the metals exactly where they are and swap the non-metals. That way you don't mix anything up. So I'll write aluminum, I'll skip some space, and I'll put calcium. Okay, see, I put them in their same spots, just on the other side in the product. And then I switch these nonmetals. Aluminum carbonate plus calcium iodide. Oop, didn't mean to put that 2 there. Sorry about that. Now we have to check oxidation numbers. Aluminum's oxidation number is +3, carbonate's -2. Crisscross and use them as subscripts. Put a 2 there and a 3 there, and I can erase those above, those superscripts. Calcium's oxidation number is +2, iodine's -1, crisscross. That's why I put that 2 there. I was jumping ahead. You'll do that eventually, I promise. Okay, now I get to balance the equation. I have 1 aluminum in the reactant, but 2 in the product. So go ahead and try a coefficient of 2 right there. I'm going to erase some of that. Then I go to my next metal. Calcium. 1 calcium, 1 calcium. Good. How many iodines is that? 2 times 3 is 6. Well, I need 6 over here, so I'm going to use a coefficient of 3. 3 times 2 gives me 6 iodines, 6 iodines. Well, over on this side, I only have 1 calcium, but I have 3 here. So I use a coefficient of 3 right there. 3 calcium, 3 calcium. 3 carbonates, see, carbonates right there. It's together. 3 carbonates there. So that equation's now balanced. All right, barium bromide plus sulfuric acid. So we're going to swap the nonmetals. We're going to swap bromine and the sulfate here. Okay, so you'll put the barium, skip some space, and put the hydrogen. Swap those nonmetals. So that'll be barium sulfate plus hydrogen bromide. Okay, let's check oxidation numbers. Barium's oxidation number is +2, sulfate's -2, so I don't need subscripts. Hydrogen's +1, bromine's -1, so I'm all done there. I simply need to balance the equation. And if you look on this side, H and the Br both have a subscript of 2, so I can just use a coefficient of 2, and it's all balanced. So let's go to this last one, calcium hydroxide and nitric acid. So we've got it written out here for you. Calcium hydroxide plus nitric acid. So calcium, put it right here, and skip some space, and we'll put the hydrogen. Okay, we'll swap those nonmetals here. Calcium nitrate and HOH. What's HOH? It's water. Alrighty, so calcium's oxidation number +2, nitrate -1. So you need a subscript of 2 right there. I can erase those superscripts. Hydrogen's +1, hydroxide's -1. So we don't need any subscript on that water. But you need to balance the equation. 1 calcium, 1 calcium. 2 hydroxides. Whoop, just 1 hydroxide. I'm going to put a 2 there. 1 hydrogen. Oh, 2 nitrogen. 2 hydrogen, sorry. Put 2 there. So 2 hydrogen, 2 hydrogen. 2 nitrates, 2 nitrates. So it's all balanced. That worked out well for us, didn't it? Okay, so these double replacement reactions, sometimes they work, sometimes they don't. And the reason we say they may not work is because we're looking for a solid product. If you get only aqueous products, that's really not a reaction. You're looking for something magical. You're looking to put 2 liquids together and make a solid, because that just doesn't happen. So you're looking for that wonderful, magical, solid product, okay? This is your solubility rules. At the top, we have things that are soluble in water with their exceptions. On the bottom, we have things that are insoluble in water with their exceptions. So we're going to use the solubility chart to help us with these reactions. So zinc sulfate plus strontium chloride. So we're going to write this whole thing out. We're going to put it into symbols. Zinc sulfate is SO4. Zinc's oxidation number is +2. Sulfate is -2. So I don't need any subscripts on that. Plus strontium chloride. Strontium is Sr. Chlorine, Cl. Strontium's +2. Chlorine's -1. So we'd crisscross those and get that. Okay, so we've written the first part of our double replacement reaction. I'm going to leave those metals where they are on this side. Zinc plus, and then put strontium. And then I'm going to swap the nonmetals. Okay, so this will be zinc chloride plus strontium sulfate. Zinc has an oxidation number of +2, chlorine -1, so we'd crisscross those. Strontium's +2, sulfate's -2, so no subscripts on that. I need to balance the equation, and 1 zinc, 1 zinc, 1 sulfate, 1 sulfate, 1 strontium, 1 strontium, 2 chlorines, 2 chlorines. That thing is balanced. Okay, so now I want you to look at the products only. These guys right here on this side. So we need to check and see, is zinc chloride solid or aqueous? Well, let's find the chlorides. Here's the chlorides. So chlorides tend to be soluble in water unless they're silver chloride, lead chloride, or mercury chloride. Well, that's not. So what that tells me is this thing is aqueous. It will dissolve in water. Let's go find the sulfate, strontium sulfate. Okay, where are the sulfates? There you go. Sulfates tend to be soluble in water unless they're strontium sulfate, barium sulfate, lead, or mercury sulfate. Well, this is strontium sulfate. Okay? Sulfates are soluble unless it's strontium sulfate. So that means that that's a solid product. That is truly magical, and we're happy this reaction occurred. All right, aluminum iodide. Aluminum iodide. Okay, aluminum's oxidation number +3, iodine's -1, so crisscross, Ali3, plus calcium carbonate, calcium and carbonate, CO3. Calcium's got an oxidation number of +2, carbonate's -2, so I don't need subscripts there. So we'll swap those partners out. So we'll leave aluminum here, plus, and then calcium. Let's swap these negative ions. Let's get aluminum carbonate plus calcium iodide. Oxidation numbers. Aluminum's +3, carbonate's -2. So we'll crisscross those. Okay. Calcium's +2, iodine's -1. So we'll crisscross those. And we now have, that's a 2, and that didn't look like a 2. So let me fix that for you. Okay, well, we've got our compounds made. Now we need to balance the equation. 1 aluminum here, 2 here. So let's start by putting a 2 there. Our aluminums are balanced. 1 calcium, 1 calcium. Oh, good. 6 iodines. Uh-oh, there's only 2 there. I'll put a coefficient of 3 there. Well, that threw my calcium off, so I'll go back over here and balance out my calciums. Okay? 3 carbonates, 3 carbonates. We now have a balanced equation. So from this balanced equation, I need to look at both of these products, and I need to find them in my solubility rules. So aluminum carbonate. So I'm looking for the carbonate. There's carbonate. So carbonate is insoluble in water. Okay, it'll form a solid product unless it's ammonium carbonate or any of those group 1 with carbonate. Well, what is it? It's aluminum with carbonate. All right, well, that was not an exception. So that is our solid product. Let's check this anyway. Let's check the iodine anyway. There's my iodides. They tend to be soluble or aqueous, okay, unless they're silver, lead, or mercury. That's not silver, lead, or mercury. So you give it an AQ. Okay, there's your solid products. Okay, let's try the next one. Barium bromide plus sulfuric acid. Barium, Ba, bromine. Okay, barium's +2, bromine's -1, so you would crisscross those and make them subscripts. Plus sulfuric acid. Okay, we gave you that one. Go ahead and put that in parentheses because I like it. All right, remember to keep the positive ions where they are. So I'll put barium, skip some space, put hydrogen, and I'm going to swap those negative ions. Barium sulfate and hydrogen bromide. Barium's oxidation number is +2, sulfate's -2, no subscripts. Hydrogen's +1, bromine's -1, no subscripts. But I do need to balance, and look, you just put a 2 right there and balance that hydrogen and the bromine. All right, so let's find over here the sulfates. All right, sulfates were here with aqueous compounds. They're soluble unless they're strontium sulfate, barium sulfate, lead, or mercury sulfate. That's barium sulfate. That's an exception. So that is my solid. We can check the bromine anyway. Bromine is going to be aqueous, okay, dissolved in water unless it's silver, lead, or mercury bromide, and it is not. So you put an AQ right there. All right, so we have a complete word equation. So I wanted to do a couple of these with you. A solution of sodium phosphate combined with a solution of iron 3 chloride produces a solution of sodium chloride and solid iron 3 phosphate. Okay, take it one little bit at a time. A solution of sodium phosphate. Let's write that formula. Sodium is Na, phosphate, PO4. Sodium's oxidation number is +1, phosphate's -3. So it's going to be Na3PO4. It's going to be combined with a solution of iron 3 chloride. Okay, iron is Fe. It has a +3 oxidation number because that's what that Roman numeral means. Chlorine is just Cl, and it's always got an oxidation number of -1. So I'll crisscross, and I'll get that. So those are my reactants. Let's go ahead and write those down. Okay. It tells me what my products are, but we could do that anyway. It says that it produces a solution of sodium chloride. That was the first one I think we learned, sodium chloride. And you know that that's the correct formula. Sodium's +1, chlorine's -1. And then we have here, I'm going to write that one up here, solid iron 3 phosphate, PO4. PO4's got a -3 oxidation number. So I don't need any subscripts down here. So it's going to make NaCl plus FePO4. Okay, I need to balance the equation. 3 sodiums here. Oh, 1 there. So let's put a 3 right there. 1 phosphate, check. 1 iron, check. 3 chlorine, check. All right, now what we need to do is we need to go find sodium chloride and see if it's aqueous or solid. Here's our solubility rules. Here's my chlorides. Okay, chlorides are soluble or aqueous unless they're silver, lead, or mercury. Well, that isn't. That's sodium. So this thing is AQ. Iron phosphate. Let's go find the phosphates. Phosphates are insoluble. That means phosphates are solid unless they're ammonium phosphate or an alkali metal cation. So that means a group 1 metal. Well, let's see, what is it? It's iron phosphate. That's not an exception. So this is my solid product. All right, let's do one more on this side. Silver carbonate decomposes into silver oxide and carbon dioxide when it's heated. So silver carbonate decomposes. Silver is Ag. Carbonate, well, that's a polyatomic ion. Silver's oxidation number is +1, carbonate's -2. So I'm going to crisscross those, and my formula will be Ag2CO3. It says that it decomposes, so that is my only reactant. And it decomposes into its pieces. Silver oxide, silver's +1, oxygen's -2. So I have to crisscross those. Here, I didn't give it enough room for that subscript. Ag2O. There we go. And carbon dioxide when it's heated. You know carbon dioxide. It's CO2. Well, let's balance. 2 silvers, 2 silvers. 1 carbon, 1 carbon. 3 oxygens. Look, 1, 2, 3 oxygens. Bam. Okay, so let's go over here and see if we can tell if we've got a solid product at all. Silver oxide. Oh, nope, we don't, because it's not a double replacement. God, what a dummy. This is not a double replacement reaction. It's just a simple decomposition reaction. So we didn't have to use that at all. You'll use the solubility rules. With double replacement D, not D. Here, I was going backwards. With double replacement. Solubility rules will go with double replacement, and then you'll use your activity series with single replacement reactions. Okay? And don't let these scare you. All right? Take them one little piece at a time. All right? Don't look at it and go, "Oh, I can't do that. That's too many words." It's always too many words, but you gotta muddle through it anyway. All right? Take it a little bitty piece at a time, and I know you can do it.